All right, good afternoon, everyone. So let's just briefly recap where we were last time. So one of the main things we learned is this general recipe for how we approach machine learning, which is here applied to simple linear regression. So first we have our model, which in this unit is this simple model that relates our feature to our target, and it gives us this prediction here. Then we want to essentially adjust or optimize the values of those coefficients, beta 0 and beta 1, based on the training data that we have, which is given by this. And then we want to, in particular, minimize some loss function. We have decided that residual sum of squares is the loss we want to minimize in this unit. And then the last thing, which is what we're going to work more on today, is finding exactly those coefficients, the betas, that minimize this loss on our data set. So in preparation for figuring out how to do that minimization, we learned about a few simple statistics. Again, statistics are summaries of the data, and we'll see that we can go through the derivation of those betas, the optimal betas, and we can use these statistics to greatly simplify our derivation and actually give it a lot more meaning. So we first learned about the sample mean, which is just the average of a set of quantities xi here. So we call that x bar. We can do the same thing for our targets to get y bar. Then we have the sample variance, which is the average squared deviation from the mean. So we have that for both x and y. And then finally, there's one more quantity that we need, which is the sample covariance. And this is the one that tells us how related the x's and the y's are. So we subtract the mean from either, then we take their product and we average it over the data set. We also learned briefly about the correlation coefficient, which is this quantity divided by the standard deviation of x and y, which has the effect of making this correlation independent of the scaling on x or y. So if you double x or double y or double both with the same data set, you won't see any change in this correlation coefficient. This correlation coefficient here is limited from -1 to 1, and it's very interpretable as a result. So then we have this, we briefly also found out some nice expressions, which we'll use in today's lecture, that if you take the average of the squared value in a data set, that's like taking the variance and adding the mean squared. And there's a similar version of this which works with cross correlation or cross covariance like this. And we summarize everything in this table. All right, any questions on what we did last time? Okay, great. So let's move ahead to solving this optimization problem. So the approach we're going to use here, and we're going to use this over and over again throughout the semester, is we are going to find the location that minimizes the gradient of the loss with respect to the parameters. So let's unpack what I just said. So in this case, we have a nice simple problem where we have two parameters to design, beta 0 and beta 1. We can then visualize with a 3D plot like this. If you see, this is beta 0, this is beta 1. We can visualize this is the loss, which is RSS. We can visualize what that looks like. So again, we want to minimize our loss, right? We want to find the betas that are right at the bottom of that. So there's some values which are at the bottom. And one of the special things about the bottom of any curved shape like that is that when you're right at the bottom and you look at the slope in any direction, it's 0. Does that make sense? And when you're right at the bottom, it's flat. If you go a little bit one way, it goes up. If you go a little bit the other way, it goes up. So right when you're at the optimal, the slope is 0. And it's 0 in any direction you look at. So we're going to look at two directions in particular, the directions that are parallel with the coordinate axes. So we're going to look at the slope with respect to beta 0. That's this quantity here, and we're going to look at the slope with respect to beta 1 of this function that depends on the two betas. And what we want is we want to set both of those quantities to 0. That's when we know that we're at the optimal solution. Okay, is that idea making sense? Because that's the main idea. And we're going to do this later with all sorts of different loss functions that don't look like this, but this is what we're going to keep coming back to. There are a few limitations with this approach. If you're dealing with a non-differentiable loss function, something where you can't take a derivative, then obviously this falls apart. But we're going to, in this right now, this works because this is differentiable. Question?
Can you clarify what you used to get the graphic shown?
Where this picture comes from?
Yeah.
So this leads me to another point, is that it turns out that this function RSS for us in this unit is a quadratic function of beta 0 and beta 1. So if you expand it, well, we're going to do this just in a moment, but if you write this out and you look at all the dependence on the beta 0 and the beta 1, you're going to have one term that's beta 0 squared, another term that's beta 0 times beta 1, another term that's beta 1 squared, and then maybe some other terms that like a constant term. So this is a quadratic function. And when you look at a quadratic in one dimension, it looks like a parabola, right? So this is a quadratic in 2 dimensions. It's called a paraboloid. It's just like a 2-dimensional extension of a parabola. So if I'm looking at it from this direction, I'm looking at the variation with respect to beta 1. It looks like a parabola. If I'm looking at it from this direction, it looks like a parabola in beta 0. But it's kind of this paraboloid. Okay, so that's where we got this shape. And there's another important thing about this shape, that it's curving up. If I had a parabola like this, and I looked for the location where the slope goes to 0, where would it be? Top, right? And if I'm interested in minimization, that's not where I want to be. That's actually the worst location. That's the maximum. So what I really want is I want that my parabola curves up. Then when I look for the 0 slope, I know I'm at the minimum. So that's another important idea. When we extend this to multiple dimensions, it's not as simple as taking a single derivative or a single curvature, a single second derivative. We actually have to look at something called the Hessian Matrix, which is a matrix of second derivatives. We won't get into the details now. We'll get into this a little bit later. But what we want is that Hessian, which is a matrix, satisfies the equivalent of positiveness for a matrix. And when you say I have a matrix, I want it to be positive, you mean that it's positive semi-definite, which is meaning that if I have a matrix, let's say H, and I multiply it on either side by a vector A, and that vector can be anything, then if this is positive definite, no matter what A is, this is always greater than 0. So we're going to see these ideas come up later in the course. I don't want to get super bogged down with them now. The main thing for now is just to realize that we have a very friendly problem. It's a parabola. It's going to be pointed in the right way, pointed up, and we just need to figure out how to set these quantities to 0, and when we do that, the optimal betas will pop out. Okay, is everybody with me so far? Okay, great. So, and also here's another visualization that's important. So if you look at these shapes down here, these are what are called the contours. They're the locations where the cost has exactly the same value. So if I took a slice of this cost at some height, you would find that it has some kind of contour at that height. And that is shown by those ellipses down below. When you have a paraboloid, the equal cost contours are always ellipses. And we're plotting those same ellipses down here, but we're also plotting these little arrows. And the arrows is actually this vector. This is called the gradient. The gradient is the vector of the partial derivatives. Since we have 2 parameters, our gradient will have 2 entries in it. And these little arrows down here show you their direction shows you the direction that that gradient vector is pointed, and the length of them shows you the norm, or the length of that vector. So what you notice is that as you get farther from the center, these things get longer, right? That's to say that if you have a paraboloid and you get farther from the minimum, it gets steeper and steeper and steeper. The slope keeps increasing as you get further out. And once you get closer to the center, you can see that the length of the arrows shrinks. And if you're right at the center, right at the optimum, it's exactly 0. So these arrows hopefully help you visualize a little bit this quantity here. And one other thing to notice is that the arrow is always going to be perpendicular to that cost contour. Meaning if you're right at that cost and you're looking for the steepest way uphill, it's going to be perpendicular to the cost. Okay, maybe that makes sense. Okay, so that's kind of the plan. And I'm just going to kind of tell you the summary right now of the expressions we're going to derive, but we're going to derive them on the next few pages, but let me just kind of write them here. So through this procedure, we're going to figure out the beta 1 is going to be sxy over sxx, or we can also write that as rho xy sy over sx. And we'll find out that beta 0 is y bar minus beta 1 x bar. Okay, so let's see why that is. Okay, so again, our objective is to solve these two equations right here. We want to set the partial derivative with respect to beta 0 equal 0, and we want to set this one, partial derivative with respect to beta 1, we want to set that to 0. So let's first do this partial differentiation here. So what we need to do is we need to do d beta 0 of, now I'm going to plug in our loss function, and I'm going to expand it so that it depends on the betas. Okay, if you remember this thing here, this is minus y hat I. That's the prediction that you get from xi when your model parameters are beta 0 and beta 1. Okay, so something we're going to do over and over again in this course is take partial derivatives. So we need to take the partial derivative of this big expression with respect to beta 0. So the first thing to remember is that differentiation is linear, meaning that if you differentiate a sum, that's the same as taking the sum of the derivatives of the things inside the sum. So we can move this through that summation sign and work on what's inside. Okay, the next step is we have to take the derivative of this whole quantity here. So for this, we're going to use the chain rule. We first take the derivative of that squared thing. That's going to give us a 2. So we're going to get a 2. Again, we're working inside the sum now. So we get 2 times the quantity. This is how the chain rule works. 2 times that quantity. And then we take the derivative of the quantity. So we take the derivative of this whole thing with respect to beta 1. Sorry, we're doing beta 0 right now. With respect to beta 0, and what do we get? Minus 1. So that's going to give us a minus to put out here. Okay. So again, we move this derivative through the sum. Then for this, we use the chain rule. We have 2 times this times the derivative of this with respect to beta 0, which is minus 1. Okay. Let's do it again for the term below. But now we're going to do it with respect to beta 1. So you got to write everything out again. It's the same, but taking a derivative with respect to beta 1. Let's think about what happens this time. So we're going to have our sum. We move this through the sum, so we have the sum over here. And then we work on this with the chain rule. We're going to get a 2, like before. We're going to get that inner term. Like before. But then the last thing is I need to take the derivative of this with respect to beta 1. What is that going to be? Derivative with respect to this, derivative of this with respect to beta 1? Minus xi. Okay, so there's a minus out here, and there's an xi here. The xi needs to be on this side of the sum. It wouldn't make any sense to put the xi out there because I is something that's sort of like private to this sum. It's only defined inside the sum. Okay, is everybody with me so far on this? Okay, the rest is a little bit of massaging of these quantities to make them recognizable. So in particular, what we're going to do is we're going to multiply both sides by minus 1 over 2n. The consequence of that will be to get rid of the minus signs, to get rid of the 2's, and to put in their place a 1 over n, which will make this look like an average and this look like an average. So let's start with the first one. Starting with the first one, I multiply the left by minus 1 over 2n. That doesn't change anything. It's a 0. I multiply the right by minus 1 over 2n. That changes this to 1 over n. So we have this term. Now, let's expand this out. We can apply this averaging to yi, to minus beta 0, and to minus beta 1 xi. So the first term, when I apply it to yi alone, we get this familiar quantity y bar. Second, what happens if I average minus beta 0 over I? Nothing. So I get minus beta 0. Third, I'm averaging this. So now the minus beta I comes out, and I have the average of xi, which we know as x bar. So we're almost done. We can now just kind of see the solution. We have 0 equals y bar minus beta 0 minus beta 1 x bar. So if I want to find what beta 0 is, I can write that in terms of the other quantities as beta 0 equals y bar minus beta 1 times x bar. So this is the first of the two equations that we had up above in the previous page. Okay, so this tells you the optimal beta 0, but it's in terms of the optimal beta 1. We don't know what that is yet. So that's the next part. We have to plug this in to what we have, get rid of the beta 0s, and then solve for the beta 1. Are there any questions so far? Okay. So we're going to start with 2, and we're going to do the same thing. We're going to multiply both sides of this equation by minus 1 over 2n. So we're going to get 0 on the left side, and then this is going to change to 1 over n on the right side here. And now we can do the same thing where we get the average of this. That gives us this term. And then we get the average of xi beta 0. That's going to give us minus x bar beta 0. And finally, we get the average of xi squared times minus beta 1. So as you can see, these are the quantities we're stuck with that we have to work on a little bit more. Do those quantities look familiar to you? We saw them just over here. So we know we can plug in those things. Okay, so okay, let's work on things a little bit more though. So what we need to do is we need to plug this beta 0 in here, and that will get rid of the beta 0 and will give us some other quantities. As you can see on the bottom here, one of the other quantities you'll get is this x bar y bar, which is here. And then we're going to have, we're also going to have like a beta 1 x bar squared. So that is going to be over here. Okay, and so now that we have this sum minus that, we can use that equation that we saw a few pages back and realize that this is just S sub xy. This is the covariance between x and y. This is not the normalized one, not rho xy. This is the unnormalized one. And on the right, does anybody remember what that's going to be? It's the variance. We can write it as sxx or sx squared, either one. And now that we have it written this way, you can see exactly what beta 1 is, right? If 0 equals this minus beta 1 that. So we can just invert this to get beta 1. We find that beta 1 is sxy over sxx. Okay, and that's the second of the two equations that we saw up here. All right, so everybody good so far? Okay, so the point is we were able to kind of do this machine learning, so to speak, in two stages. We take our data, we squeeze it down to 5 numbers, and with those 5 numbers, we can design our beta 1 and beta 0. That's what we can do in this simple case. You usually can't do that, but we could in this case. That's what's nice about quadratic RSS and so on. But there's one other thing we would like to know. We'd like to know what the minimum error is, because this tells us how good our fit is. In addition to figuring out what the optimal betas are, we want to know, did we solve the problem or not really? Do we have a good predictor or not really? So to figure out whether we have a good predictor or not, let's look at the minimum value of the RSS. So we're gonna take our definition of RSS, which is this one, right? And we're gonna plug in the optimal beta 0 from the previous page. That was this one. And if you do that, you're gonna get a y bar here and a beta 1 x bar. So that's all that happened is we gained those terms. And now you can see we're almost ready to plug in our optimal beta 1, but let's just expand this quadratic first. It'll make it a little bit easier. So we have a sum of this minus this squared. So we can look at the sum of the first term squared, that's this. We have a sum of the second term squared, that's this. And we have the cross terms, 2 times this. Okay, and when you look at these equations, does anything pop out at you from this? What is this? The average value of y minus its mean squared. The variance. This is the variance of y. So we can call this, actually, we're missing the 1 over n in front, so it's going to be n times SYY. N times the variance of S, or variance of y. What about the middle brace? SXY. So again, n times SXY. And the last one? SXX. Okay. So now we have actually a pretty concise expression for the minimum RSS as well. So this is what we have so far. So we have, we also have to plug in beta 1. And that's going to put some more SXYs and SXXs in. So in particular, we're going to get all these terms have an n. So we can put the n out front. And then we're going to have SYY minus 2 times SXY times another SXY divided by SX. So that's this. Oops. This one. And then finally we have, we're going to square this guy. So that's going to give us sxy squared on the top. And then we're going to have this squared on the bottom, but one of these will cancel. So we get sxx. And now you can see that the last two terms are actually scalings of the same thing. So they boil down to this. And we can make this even a little bit more interpretable if we pull out the syy out front. Then we have 1 minus this divided by syy. Does anybody recognize what that is?
Correlation coefficient.
Correlation coefficient squared, right? Because there's a square here, and this is like a squared standard deviation, squared standard deviation. So you actually get n times 1 minus rho xy squared times syy. Okay. So this is actually pretty insightful. Does anybody see how you could get RSS equal to 0? N is equal to 0. Okay, what does that mean?
Well,
It means you have no data. You have no problem to solve. Okay, so that's not a good one. What's another way to get RSS equals 0? Rho xy equal 1, right? That's when x and y are the same up to a scaling. So they're like, y is completely predictable from x. That makes sense. Completely predictable, we can get the prediction error to 0. Someone else might have said, make syy equal to 0. What's the interpretation of that? What does that mean when syy equals 0? What do the targets look like?
Like straight exactly fit your curve, your line.
They're all the same. There's no variance. That means they're all equal to the mean. That's a very boring problem. The target is always the same. Yes, of course you can predict it. You can predict it no matter what your x is, what your features are. It's always the same. So that's not very interesting. The most interesting thing here is that if, I would say if the correlation, normalized correlation is 1 or -1, either one, you can predict it perfectly. Anyway, just give some intuition about predictability. And we'll come back to this very shortly. So any questions on this derivation? Okay, so let's move on to back to the demo, interpreting this. So here we computed the mean of x, the mean of y. We computed the variance of x and the variance of y, as well as the covariance. And a student actually asked after class the other day, why are we not using np.var to do this? And the reason is because different packages, when you compute the variance, they'll use either the biased or the unbiased version of the variance. The unbiased one uses 1 over n minus 1. And that is not something we used. If you actually use that, you get the wrong number. So because I don't remember what the variance of how np-var is computed, it was safer to just use mean because I know exactly what's going on with mean. And I think that's a good rule. Don't use a command unless you're absolutely sure what it does. And to be absolutely sure, go check the documentation. But some commands work in multiple ways. Many are, it's equally common to use the unbiased and biased ones, so I don't know what it defaults to. So anyway, that's how we computed all these 5 statistics. Once we have them, as you can see, it's very easy to get beta 0 and beta 1. So, and it turns out that these numbers are, 39.94 minus 0.16, whatever. But what this allows us to do now for our data is to plot our regression line, which you can see does a reasonable job of predicting the data, the miles per gallon from the horsepower, but obviously it's not perfect. Maybe we could do better if we use some sort of model like this, and we're actually going to talk about that in the next unit. But for now, starting super simple, we're just fitting lines. Okay, so that's sort of concluding the demo. If you would like another nice, simple demo well explained. There's a link here. It's a pretty nice demo. It's very similar in spirit. And now, the very last thing I want to talk about is being a little bit more precise about fitting the model, about assessing goodness of fit. In other words, did we do a good job fitting it or not? That's useful because when you're working with data and you've done a fit, the question is, do you stop or do you try another model? Are you happy or not? So we have to be specific about being happy or not. So we're going to use, so for linear fits, what people always seem to use is this thing called R squared. So I'm going to describe R squared in a simple way. There's a much more kind of long and complicated explanation which you can find at this Wikipedia page. But let me describe it in what I think is a simpler way. So again, our objective is to judge whether a predictor is doing well. So first you might say, well, shouldn't we just look at RSS? Because we know if the predictor is perfect, RSS is 0. And if it's imperfect, it's going to be greater than 0. Is that enough? And I'll say, well, there's a couple problems with RSS. So let's come back to the definition, or this is what we have for RSS of the optimal solution. And you can see, number one, it depends on the number of samples. So as your data sets gets larger and larger, RSS gets larger and larger. So this is sort of inconvenient, right? Maybe we should normalize by n. We should look at RSS divided by n. And now this quantity will not grow with the data set size. It'd be a little bit easier to interpret. So that's one thing we're going to do. But that's not all. There's also this quantity, SYY. It says that the more variation there are in your targets, the higher your RSS is. So, and the variation in the targets really has nothing to do about the relationship between X and Y. It's just how much variation there is in your targets. So that also makes RSS a little bit hard to interpret. So in addition to dividing RSS by n, I say we should also divide by SYY. And this would give us a normalized RSS. So that's the idea here. Let's use a normalized version of RSS. We're going to divide by n, and we're also going to divide by the variance of y. Okay, and this is almost what's done in R squared. We're going to talk about R squared because it's the way that it's always written up in books. And so I just want you to know exactly what R squared is. So R squared is 1 minus this normalized quantity. Okay. So this is defined as the quantity R squared. This has this name, the coefficient of determination. If you read the Wiki page, you can see why it's called that, but it's not that important. What I think is more important is how to interpret RSS. So let's take a close look at RSS. So if you get an R squared, interpret R squared. If you get an R squared of 1, what does that mean? It means that this is 0, right? If R squared is 1, it means this must be 0. The only way to get this 0, we just talked about this, is for RSS to be 0. That's perfect prediction. That means you are, your y hat is perfectly at y. That's the best possible case. You can't get any higher, right? Because I can't make this negative. Because RSS is a sum of squares quantity, you can never make it negative. So the best you can do with R squared is 1. Okay. Let's talk about the worst you can do. So if you're using this least squares optimal design, what's the worst that can happen? Let's come back to this equation for RSS. What's the worst that can happen with this to give you the lowest possible RSS? What if my x's have absolutely nothing to do with my y's? I just drew x at random, I drew y at random independently. What do you expect is going to happen with these quantities?
Orange.
What's this one going to be? 0, right? That's the worst possible thing that can happen for the optimal predictor, is that there's nothing to predict. So if this is 0, then RSS is just n times SYY. Oops. When RSS is n times SYY, this whole thing goes to 1. 1 minus that goes to 0. So the way to interpret this is that the predictor is no better than the trivial predictor. So what does a trivial predictor do? It ignores the data x. It just looks at the targets y. And it just predicts the mean value of the targets. No matter what x is, it just says y is at its mean. You can always build that predictor, right? And that predictor will always give you r squared equals 0. No better, no worse. And you can do that even if x has nothing to do with y. So that's sort of the other extreme. And that's the worst thing you can do if you use the optimal predictor. But is that the worst thing you can do for any predictor? No. So sometimes what you'll find in your first lab is you're programming your least squares, coefficient calculation. You make a mistake, there's a bug in your code, and you get negative r squared. So that's worse than trivial. It's definitely possible. You can make a predictor that's worse than trivial, but that's just because there's a bug in your code. Or because maybe you didn't know about least squares design. You came up with your own design and it was a bad idea. Okay, so it is possible to get negative r squared, but not if you use the least squares optimal predictor. In that case, the worst you can do is r equals 0. Okay. Let's do one last thing. Let's plug in, this is our RSS equation. Let's plug in the least squares coefficients. If we do that, if we plug in the least squares coefficients, we get this. That's what we derived. And if we plug this expression into here, and you can see we're taking RSS, we're dividing by n, we're dividing by s squared y. We're taking 1 minus that. All that's left is rho xy. So squared. So actually, r squared is nothing more than rho xy squared. Okay, so that's another way of interpreting r squared. It's really just this normalized correlation coefficient squared. Okay. So that's it for all the math. Let's just take a look at another visualization about, since really it all boils down to rho xy squared, at least for the optimal predictor. Let's take a look at some of the data sets that have best case data sets. So this is data sets that have rho xy positive, negative, 0. In that case, you have pictures like this. In all these cases, the goal here is that these lie along a line, and you have perfect prediction in all these cases, right? Okay, this is a picture we saw before. This is varying our xy's from 1 to minus 1. These guys will both have a RSS of 0, r squared of 1. This one in the middle, this will have an RSS of, it depends on the data, but it will have an r squared of 0. But that's not the only way you can get an r squared of 0. Here's a number of other examples of data sets where there's structure, but there's no correlation. So in all these cases, as a human, you can look at this and you can say, yeah, it's actually a lot of structure there. Maybe I could do some sort of prediction, but the kind of simple prediction we're doing here, linear prediction, is not really going to be good enough. So this is not the only way to get rho xy equals 0. Here's a whole bunch of other ways. In order to leverage those things, we're going to have to use more sophisticated methods that are not based on correlation, but based on some other more complicated things. All right. Any questions on this page? Okay. One last one last experiment. So what we did in our demo was we predicted, this was our miles per gallon versus horsepower. We predicted this. We said we wanted to predict something like this. Well, here's a simple way we can do this while still using all the tools from this section. Instead of predicting miles per gallon, why don't we predict inverse miles per gallon? Turns out that if you plot this scatter plot of inverse miles per gallon, it looks like this, which, as you can see, is a very nice linear shape. So we just take our data, we pre-process our data by inverting all our targets. We predict this guy, and then once we get our prediction y hat, we invert that. And we get back miles per gallon. If you do that, you actually get this curve. So the point is that even though linear prediction seems really simple and crude, actually if you combine it with a little bit of data manipulation, it can actually be pretty sophisticated. The downside in this particular application is that some expert had to tell us to do this. It's not obvious that, among all the possibilities of nonlinear data transformations that we could have done, it's not obvious that we would have ever thought to try this. But, in this case, someone was clever enough to realize this, and actually it works really well. So what we're going to do in later chapters is we're going to try to figure out how to learn how to do things like this, not have an expert tell us about them. But for now, the point is that linear prediction, maybe as just the end technique, is pretty powerful if you allow other data transformations to happen beforehand. Okay, and so you'll have on your first homework, you'll have a problem like this where you'll have to look at an equation and figure out, it's pretty easy if you look at it the right way, how to do this transformation to make it linear. Okay, all right, so that's it for this unit. So the next unit, multiple linear regression, is very similar in spirit. It's just mathematically extending to more than one prediction variable. That's all. So we're going to see a lot of the same concepts. We're going to have another data set, different data set, one that has several variables, and it's this diabetes data set, which is a very popular data set for intro machine learning courses. It's motivated by the fact that diabetes is it's a really important disease. It kills a lot of people, so maybe we should see if we can predict things. Can we predict, the progression of the disease given things like age, sex, body mass index, blood pressure, various other biometrics? So there's a little bit about the data set. This data set has 442 instances. This basically means this is what n is, the number of samples in the data set. This has 10 different attributes. Remember, attributes are features. Those are the things we're using to predict. There's 10 of them. And in fact, this is what they are. Age, sex, body mass index, blah, blah, blah. And then there's this 11th column in the data set, which is the target, which is a quantitative measure of disease progression 1 year after you measure these quantities. You want to see, is that person going to get sicker or not? So that's the data set. This data set is very easy to load because it's built in to sklearn. sklearn is the main package in Python for classical machine learning type stuff. Has tons of methods. We're going to use it for many, many units until we get to deep learning, and then we need to go beyond sklearn because it doesn't have stuff for deep learning. But basically, what's nice about this data set is it's built into sklearn, so it's super easy to load. You just import this datasets subpackage, and then you do datasets.load diabetes, and it puts the data into this structure, and you can pull out the features. We'll call them X, pull out the target, call them Y. And this actually is going to be a matrix for us, and this is going to be a vector. We're going to talk a little bit more about how we structure those in the next couple slides. But if you want to examine the size of this quantity in NumPy, you do dot shape, and that will return the number of rows, which is 442, and the number of columns, which is 10. And if you remember, that matches this, 442 rows, 10 columns. Okay, so, yes. Question?
Yeah, so about that 11th column, what are possible values of that?
So that's going to be some quantitative measure of degrees of progression. So it's going to be some real number. I don't know exactly what this measure is. Probably have to go back to the original paper from which this data set came from to see exactly how they define that. But it's some quantity we want to predict. Basically, that's all that's important for us. Okay. So when we work with a lot of these concepts, it becomes very tedious to deal with all these different dimensions in our data if we don't use quantities like vectors and matrices. So this is why, in part, linear algebra is so important, because it's a tool, it's a way of describing our data. It's just really fundamental to what machine learning is. So we want to put all our feature information, all the stuff we're using to predict, we want to put that into a matrix X, and we want to put all our targets into a vector Y. And here's several views on how we can think about this matrix. So you can think about this matrix X. This is as you go down the rows, you can see that you have a total of n rows, right? Each one of these is a row. You have n rows, and remember, n is the number of samples in our data set. When you look at Y, you also see that it has n rows. So as you go down both X and Y, you go to different samples in your data set. Now we're only predicting a single thing, so Y has only one column. But now we have various things we can use for prediction, and those are the different columns in X. So in particular, we have D different features. That's the variable we're going to use the whole semester for the number of features is D. And like I said before, number of samples, all semester is going to be N. So this X has N rows, D columns. Now sometimes we want to talk specifically about one piece of data. So we need to extract one row of X, and we'd like to give it a name. It's a row vector, as you can see, right? So we want to give it a name, and we'll call this little x boldface sub 1. It's the first row vector. If I extract the last one, that's the nth row vector. As I mentioned the other day, whenever we define a vector in this course, it's always going to be a column vector. Like here, I'm calling this column Y. And so whenever you see something without a transpose, you know it's a column. But here we're describing something that's a row. So we need to basically, when we make a definition of x1, we're defining x1 as these quantities as if they were put in column form. And so if you want them in their original row form, you got to have a transpose there. Okay. Another convention which you saw in the homework due today is that boldface capital letters are matrices, boldface lowercase letters vectors, and non-bolded quantities scalars. Okay. So here you can see exactly, so the ith row is built like this. Here's the transpose. If we want to think about what's the ith sample in our data set, it's this guy and then the corresponding yi. So that's going to be the ith data sample. Okay, so this is how we're describing our data from now on throughout the course. And next, let's talk about how we're going to do our prediction. Again, the ideas are the same as last unit, but now instead of one predictor, one feature, one attribute, we're going to have D of them. Okay, so we have a vector of features. We call it X. So here, I'm not using I. Remember, when we start using subscript I, that's telling us the ith sample in the data set. So this is just sort of a generic quantity. There's no i's, so we don't have any subscripts here. We don't have double subscripts here. Unlike over here, we had I here and we had all these i's over there. So this is just kind of a generic vector of features that you might see later once you're done fitting your model. It's not part of your data set. So again, D features, there's D of these things we're using for prediction, not just one. So that means that our model is going to look like this. So we're saying that the target is approximately equal to an intercept coefficient plus some beta 1 times x1, beta 2 times x2, and so on, all the way till beta d times xd. It's just growing the model from last time. And finally, we're going to define this sum as our prediction y hat. So here we have an equality, here we have an inequality, because our prediction is not exactly perfect. In the last unit, we had 2 coefficients to learn. Now we have d plus 1 coefficients to learn, all these different betas. So the key question for this unit is, how do we choose all these different beta vectors for our given data set? Okay, so to prepare us a little bit, we're going to find that it really helps to, again, write our model using vectors and matrices. So for this, we need to grow. This is how we defined x, if you remember. This was like our boldface x from a couple pages ago, our X matrix, right? But notice that I augmented it by adding a column of 1s in the front. The reason I'm doing this is I want to capture the role beta 0. In particular, I'm writing my prediction as matrix A times vector beta. Actually, let me be a little more consistent. Sorry, when I write the notes and I want to do boldface, since I don't have a good boldface font, I'm going to put an underline under anything that's boldface if I typeset it. So let me go back here. Actually here, let me put an underline under this X. Okay. So rather than writing things like this, which is kind of tedious because there's all these different X's, I want to write things, actually this is what I'm writing now. So I'm writing the prediction for the ith data sample as beta 0 plus all these other betas times their respective features. And I want to write this actually for all the different i's, starting from I equals 1 all the way through I equal n. So I'm going to stack these into a column vector. So the first one is going to be y hat 1 all the way at the end y hat n. And I want to write this efficiently using a matrix vector multiply. So hopefully you can see that by adding this column onto A, when I do this A times B, I'm going to get beta 0 multiplying the first column, plus all the other beta coefficients multiplying all of these columns. And so that's why I'm adding this augmented column to capture the effect of beta 0 on the prediction y hat. Is that making sense? Okay, so this is the prediction on my training data. But that's not all I care about. What I actually really care about in the end is once my model is trained, someone's going to give me a new X I've never seen before. It's not in my training data, and I want to apply my model to that. So this is that new X. This is how I'm going to write the prediction on that new X. And similar to what I did above, I'm going to make a row vector that's going to have a 1, and then it's going to have X transpose, and it's going to multiply that times my beta vector. Okay, So this beta vector is built like this. So it has a top coefficient of beta 0 that's going to multiply this. And then all the other coefficients in beta will multiply the respective coefficients in this transposed x. Okay. So being able to visualize and understand this is obviously important, and that's what the homework 0 is supposed to try to get your head warmed up for, just seeing how these vector matrix relationships works. Because if you can't see them, then all the notes turn into gibberish. So it's super important. And if it was difficult, if you're not still comfortable, I suggest this is a great time before your semesters get really busy to keep trying to learn that linear algebra stuff, because we're just going to keep using it more and more and more. Okay, so again, this is prediction on the data. This is prediction on some new feature vector x. This is a generic function of some new x, but it's again involving the beta coefficients. And what we want to do is figure out how do we learn these to minimize, again, RSS. So we're going to work out those details on Wednesday. This is a good point to stop for today. Are there any questions on anything on this page? Yes.
How do we interpret, I guess, the bias, like B0 and all that?
B0, yeah, so B0, basically, this is what we're going to have. This is like a generalization of what we saw. Before we had a line, now we're going to have a plane.
Yeah.
B0 is just the height of the plane. Before it was the height of the line. Now it's the height of the plane. Okay, we'll talk about this on Wednesday.
Okay.